Welcome back. Welcome back to my backyard. So this is our lesson 2 of the week. This one is on percent yield. In the first lesson, what we learned about was excess and limiting reagent. And so the point of that lesson was to figure out, when you're given 2 reactants, which one of the 2 is going to limit how much product you can make, right? What's the maximum amount you can make, because the reactants that you have, they're not necessarily in the correct proportion. So you may have too much of one, and that would be your excess reagent. So the amount of products that you can make, that is always determined from the limiting reagent. And so using the limiting reagent, you find out how much product you can make. That's the lowest amount that you're going to be able to produce. And that's your theoretical yield. So this amount tells you that in theory, you could make up to that much. In actuality, right, the actual yield is what you would actually obtain in the lab. If you did the reaction, how much are you actually going to get? And so what we're going to learn about today is the percent yield, which is simply the percentage of what you got compared to what you could have gotten or should have gotten had it gone perfectly well. So that's what the percent yield is. It's like you taking a test and getting 85% on the test, right? So you actually got 85 out of a theoretical 100%. So you've mastered 85% of the material. That's exactly what we're going to do here. The thing about chemical reactions is that you can't just make a blanket statement and just say, well, you know, I got 60% on this reaction, so that's either good or bad, or it just depends. It depends on the chemical reaction. Some chemical reactions don't go to completion, so they actually reach a state of equilibrium. And that's what we're going to talk about in the next month or so. So for now, let's focus on the percent yield. So you see on your notes, this is the percent yield notes that you have. So if you want to pause the video and open that up so that we can follow together. So in order to find, going to paragraph number 2, in order to find the percent yield of a given chemical reaction, we need to know the theoretical yield, right, and the actual yield. So again, the theoretical yield is the amount that you calculate on paper, assuming a perfect situation. This is how much you could get. So the theoretical yield is always based upon your stoichiometry calculation, what we're going to do on paper. The actual yield is what's actually happening in a real chemical reaction. The equation is right here. So to define and to calculate the percent yield, you take the actual yield and you divide by the theoretical yield, multiply by 100 because it's in a percentage form. You could calculate the percent yield using an actual yield in grams and a theoretical yield in grams, or you could calculate the percent yield with an actual yield in moles and a theoretical yield in moles. It doesn't matter which unit you use as long as they're the same, because you're going to be dividing moles over moles, or you're going to be dividing grams over grams. So the steps are, well, it's the same as the previous lesson on the limiting reagent. So we're going to balance the equation, and then we're going to find which one is the limiting reagent, and then that's going to give us the theoretical yield. And then we're going to take the actual yield and we're going to divide by the theoretical yield. So this example number 1 here, this is just a practice using the equation. It says that we have a theoretical yield of 4.63 grams. So again, that is based on calculations on paper, right? In theory, this is how much we could make. You do the experiment in the lab and get an actual yield of 3.91. And so essentially what this is telling you is that you have 3.91 out of a possible 4.63. Right? You got a score of 85 over a possible 100% times 100. So it's always actual over theoretical. So if we do this calculation, we have 3.91, and we're going to divide by 4.63. And we are at 84.4%. So that would be our percent yield, right? What the percent yield tells you again is that that's how much you obtained. So we obtained 84% of what we could have obtained. Example number 2 says that your actual yield is 0.87, so 0.87 moles. That's the actual yield. Now in this case, they want to know what the theoretical yield, and they're saying that you obtained 82%. So this amount, 0.87, is 82% of what amount, right? So 0.87 moles, that was 82% of what you could have collected. And they want to know how much is it that you could have collected. So we'll put an X for the theoretical yield. I'm dividing this 82% by 100. So I don't have to times it by 100 over here. And so 0.87 divided by 0.82, 1.061. So 1.06 grams, that was the theoretical yield. That's how much we were supposed to obtain. But since we only obtained 82% of that, that's the 0.87 that we were given as the actual yield. So what does it look like in terms of chemical reaction? Well, you'll see it's exactly, most of the steps are the steps that we did in the limiting and the excess reagent. The only thing we're doing now is we're just adding one more step at the end. Once you have established what your theoretical yield is, there's just one more division to do, and that's it. So let's do example number 3 here, where it says to consider the reaction between silicon and chlorine. Of course, the first thing we do every time is to balance the reaction. And so we're going to need a 2 in front of the Cl2 to balance the 4 chlorines on the product side. So here it says that we have 1.15 moles of Cl2 and an excess of Si. So that was very nice of them. They just told us which one is the limiting reagent, right? Because if they're saying that you have an excess of silicon, that means that the chlorine is the limiting reagent. So that saves us a lot of work on that, on the front end. So we know now to get the theoretical yield from the chlorine. So what's given to us? 1.15 moles of Cl2. We're already in moles. 1.15 moles of Cl2. According to the balanced equation, two moles of Cl2 gives 1 mole of SiCl4. Remember, the top line is always from the balanced equation. and the bottom line is what you're given in the problem. So in the problem, we're given 1.15 moles of Cl2. So what are we going to make? Cross multiply, solve for x. You see the mole ratio from the balance equation is if you start with 2, you get 1. So you get half of what you started with, right? So 1.15 divided by 2, so 0.575. So the theoretical yield is 0.575 moles of SiCl4. So all we did here is we solved for x. 2 over 1.15 equals 1 over x, and you cross multiply. You bring your x, your 1.15, and your 2 goes down. So 1 times 1.15 divided by 2 is equal to x. So this amount right here is our theoretical yield. This tells you that you had enough Cl2 to make this much product. Suppose that we run this experiment ourselves and obtained 0.457 moles. So this is our actual yield. So we actually ran the experiment and we actually got this much. So what was the percent yield? Well, very simple. And we're going to take the actual yield, which was 0.457 moles. And we're going to divide that by the theoretical yield, because that's our equation. Right? Our equation is the percent yield is equal to actual over the theoretical times 100. So divide that by 0.575 moles times 100. And we're okay because we're in moles over moles. Again, we can do this in grams over grams. Both are perfectly fine. 0.457 divided by 0.575, and we have 79.5%. So we actually obtained 79% of what we could have. Example number 4, same thing, except now they're not telling us which one is the excess and which one is the limiting reagent. So we're going to have to do like what we did in the previous lesson about limiting an excess reagent, and we're going to have to find which one it is that produces the lowest amount of product. And once you have the lowest amount of product, that's your theoretical yield. This one is in moles, which is exactly like what we did in the previous lesson. If you have any questions or need a little refresher on that, please go and listen to or watch the previous lesson that we did on limiting an excess reagent. What we didn't do in the previous lesson was doing one from grams. And so we can do that this time, and that would be example number 5. Example number 5, please pause the video and take a couple minutes to do this. Go as far as you can. Remember, you take the mass of the reactant, of each reactant, you divide by the molar mass to find the moles, you run that through the mole ratio from the balanced equation. That's going to give you the moles of product. You do that for both reactants. You take the lowest amount of moles. That's your theoretical yield. Okay, so pause the video and do this problem. Go as far as you can, and then I'll work this out with you. Okay, let's take a peek here. Magnesium hydroxide reacts with nitric acid, that's the HNO3, to form magnesium nitrate and the water. If we start with 9.7 grams of magnesium hydroxide and 15.3 grams of the nitric acid, how many grams of magnesium nitrate could we make? So the first thing we're going to do is we're going to balance this equation. We have 2 nitrates in the product. So that means that we're going to need 2 of the nitric acid so that we get 2 nitrates. Now we're looking at the magnesium, which is 1 on each side, and 2 hydrogens and 2 oxygen, and 2 hydrogen over here, and 1 of the water. So we're going to need to do a little bit of work here to balance this equation. Oops. All right. So 2H2O, and that balances our reaction. Now, the first thing that we need to do, we do need to convert to moles, because what we're given in this problem are grams. And so to get to moles, we take the mass and we divide by the molar mass. So for magnesium hydroxide, here we're going to do we're working on from the magnesium hydroxide. We have 9.7 grams. And we're going to divide that by the molar mass of magnesium hydroxide. So we have the magnesium at 24.3. Then we have 2 oxygen. So 16 plus 16, that's 32. And then we have 2 hydrogen. So 1 plus 1, that's 2. So 24.3 plus 32 plus 2. 58.3 is the, 58.3 is the molar mass, grams per mole. So 9.7 divided by 58.3, and we have 0.167 moles. So from the balanced equation, so this is going to be our MgOH2. From the balanced equation says that we start with 1, and we're going to make 1 magnesium nitrate. So if we start with 0.167, then of course it's a 1-to-1 ratio. We're going to make 0.167 moles of magnesium nitrate. So that's the maximum amount that we can make if we're using up all of the magnesium hydroxide. We have to do exactly the same calculation now for the nitric acid, because we don't know which one of the 2 is a limiting reagent. So we're going to scroll up here, and we're going to do this exact same thing again, but with HNO3. So yes, we do have to convert to moles because we're not in moles. 15.3 grams of HNO3. Again, we will do the mass divided by the molar mass. But this time it's HNO3. So we have H is 1 plus nitrogen, which is 14, plus oxygen, which is 16 times 3. and that's going to be the molar mass. And the mass was 15.3 grams. So 15.3 grams, and that's going to be divided by 48 plus 14 plus 1, 63 grams per mole. So that is the molar mass of HNO3. 15.3 grams divided by 63 grams per mole, 0.243 moles of HNO3. So then we're going to run, now that we have moles, we can use the mole ratio from the balanced equation. HNO3 to MgNO3 twice. On the balanced equation, we have 2 nitric acid, 1 magnesium nitrate. So 2 nitric acid, 1 magnesium nitrate, 0.243, and X. So we see here that our mole ratio is 2 to 1. We start with 2, we get 1. So we get half of what we started with. Which means that if we solve for X, we cross multiply and solve for X, it's going to be half of 243. So 121.121 moles of MgNO3. We have enough of the HNO3, we have enough nitric acid to make 0.121 moles. That's less than 0.167. So what that tells us is that nitric acid is the limiting reagent. This amount right here, this is our theoretical yield. That's the maximum amount we can make, because as soon as you've made 0.121, you're going to run out of nitric acid. The reaction will stop. It doesn't matter if you have enough magnesium hydroxide to make 0.167. You'll never get there. You don't have enough nitric acid. That's why nitric acid is your limiting reagent. Magnesium hydroxide is your excess reagent. Right? So that's why we don't use the numbers from the excess reagent in the calculation, because we'll never get there. Where we could get is 0.121. That's the maximum amount we can get. And then we're going to run out of nitric acid and the reaction will stop. So how many grams does that give us? Well, so we're going to take the number of moles and we're going to multiply by the molar mass of magnesium nitrate. So we would take 0.121 moles and times the molar mass of magnesium nitrate. So magnesium is 24.3 plus, then we have 2 times NO3. So 2 times NO3 is 14 plus 48, which is 3 times 16. So 14 plus 48, this is equal to 62. So this is 62, and that's the mass of NO3. There's 2 NO3s. So 62 times 2, 124. So this whole thing here is 124 plus 24.3, which means that the molar mass is 148.3. That's the molar mass, 148.3 grams per mole. We had 0.121 mole times 0.121, and that gives us 17.94 grams. So 17.94 grams, that's the maximum amount we can make. It's our theoretical yield in grams. Suppose we did this experiment. Again, we're about to be told what the actual yield is. Right? We're actually doing the experiment in the lab. We get 14.05. That's our actual yield. So the percent yield is the actual 14.05 grams divided by the theoretical, which is 17.94 grams, times 100. This is our percent yield. 14.05 divided by 17.94 times 100, 78.3%. And that's how you calculate the percent yield. I have for you some practice problems right here. I hope this helps. Now, using this information, you can go back to the lab that we did last week, the Alka-Seltzer lab. If you did not do the lab, then I would strongly encourage you to look at my video about the lab, and you have the lab handout in your notes, in your OneNote. So please take a look at that. And with this information here, hopefully it will all make sense. Thanks again for joining me. This will take care of our lessons for the week. And I look forward to seeing you again next week. We're going to talk about kinetics and collision theory. Have a great week, everybody. Thank you.